Okay, let's go ahead and take a look. On the first one, we're doing methanol with a little bit of acid catalyst. This is going to give us the acetal. Okay, I'm going to go ahead and add that hydrogen. You don't have to show that hydrogen depending on the book. They won't show that hydrogen as you go from the aldehyde to the acetal. On the second one, we have several stages, right? The first stage, we're going to do a protecting. We ended up class with something similar to this one. So since the aldehyde reacts faster than the ketone, we'll protect the aldehyde first. And then we do a reduction with sodium borohydride and methanol. And we'll look at that again today. But we've seen this one in organic 1. And then we do a hydrolysis of that acetal. Get us back to the aldehyde. Okay, questions about either of these two? The Chem 101 homework, there's 2 assignments up. One will be due next Tuesday. That's for like the first half of aldehydes and ketones. Then there'll be another one due in 2 weeks. That's for the second half of aldehydes and ketones. That one's pretty long. There's 50 problems on there because I wanted to make sure we got a thorough amount. So I go ahead and start that one. We've covered about half of that already. So you should be able to start both of those assignments. One's due in a week and the other one's due in 2 weeks. I did go ahead and correct, if you did not get the early assignments, I went ahead and added that late submissions are allowed for all of these, all the way up to the final exam. Again, once you run out of your attempts, there's no more attempts, but if you get in a bind and you can't get one done, you can always do it late with a 5% decrease. Okay, let's go ahead and move on. We're going to do a little bit less mechanisms today, but we will show a few of those. Now we're moving into nitrogen nucleophiles. So we're still dealing with the nucleophilic addition to the aldehydes and ketones. We're just changing what type of nucleophiles we're looking at. The first type of nucleophile is going to be just a primary. And again, a trace of acid just to get the reaction going. Okay, and if we take an aldehyde, we'll get an imine. A ketone will also give an imine. I exaggerate the imine, so if you ever go somewhere else and say amine and imine, as in amine and amine, the reason I say that is that in my Texan language, it's kind of hard to tell the difference between amine and amine. Okay, so I exaggerate. So don't go to Cornell like one of my students did once and say imine, because they'll give you a hard time. So don't do that. All right. So what's happening here is very similar to what we saw with the alcohol, right? We get a nucleophilic attack, and then we're going to have a lot of proton transfers. So there is a lone pair on our nitrogen that's going to attack our electrophilic carbonyl. End up with this zwitterion type species where we have a plus and a minus in the same one. Now we can get a proton transfer to to a different molecule, which is probably more correct. So let's go ahead and show that. Sometimes the book will show it in the same molecule. That's acceptable. I like to show it with something else. Again, these are all reversible. I'll bring in germ base again. In the book, I believe they showed this in one step, just deprotonating itself. Then we get to this species here. We need to do another proton transfer. So I'm going to bring in the generic acid again. This time we're going to protonate that oxygen. If we had protonated the nitrogen, we just would have gone backwards. But protonating that oxygen now gives us water. Right, so we get OH2 here, right, with the positive. Nitrogen's got the lone pair, hydrogen, CH3. Now the lone pair can come down, kick off the water as a leaving group. Now we've lost that group. And now we just need another proton transfer because we got the nitrogen positive. Electrons go back to that nitrogen. To get to the imine, okay? So if we look at this, this is a nucleophilic attack. Proton transfer. Proton transfer. Proton transfer. Loss of leaving group. Right, and then proton transfer. So we had nucleophilic attack at the carbonyl carbon, pi bond breaks. Then we get a proton transfer, right? This can be any generic proton available. In the book, they show it internal. I had a major professor that used to count that always wrong, so I tend not to show it. It really depends on your preference and the dilution of the solution. Here, we pick up this proton, right? Nitrogen goes back there. Proton here comes in, kicks off the the conjugate acid. Then we get loss of leaving group, right? Lone pair comes down, kicks off the water. That gets us to this protonated imine, and then the imine goes loses a proton to go to the stable species. Questions about this mechanism? This kind of attack, proton transfer, proton transfer, proton transfer, proton transfer, loss of leaving group, proton transfer. We're going to see this a lot throughout the rest of the carboxylic acids as well. Okay. Besides the imine formation, it turns out that NH2R group is pretty generic. So I could take the aldehyde, react it with an NH2OH, right, with a trace acid. And again, that most often is the p-tosylate or the tosylic acid, TSOH. If I have the OH here, this is called an oxime. And that has a biological derivative. I take this species with the hydrazine, I'll get the hydrazone. So there's a whole group of these. But anytime I have the NH2 with an acid catalyst, I'm going to end up with the same product. I'm going to end up with a carbon double bond nitrogen. And then whatever else is out there, this R group could be an alkyl group, could be a hydroxide being an oxime, or could be another NH2 being the hydrazone. The big difference then is when we go to secondary alcohols, secondary amines. Bless you. Okay, so if I react an aldehyde or a ketone, okay, I showed the first one with aldehydes, this one I'm showing with ketones. I'm going to go back and forth. They're interchangeable. Remember, aldehydes react faster, but both of these will be the same similar products. In a aldehyde or a ketone with a secondary amine, right? So only one hydrogen attached. What I end up with is an enamine, right? And remember, if I had a double bond with an alcohol, right, that was an enol, so similar name. It's a double bond with an amine attached to it, enamine. Okay, I'm going to give you a choice. We can go through the full mechanism, or we can assume that you know the first mechanism I just showed you, and then start from the point where it deviates. So full mechanism, raise your hand. Okay, from where we deviate. Okay, all right. So if we go back up here, right, we get nucleophilic attack, right? Then we get a proton transfer, and then notice here, right? Notice right here, this is important. We've got the nitrogen with a hydrogen and a methyl. Then we get a proton transfer, then we get attack, and then look right here, okay? This is going to be the point where we're going to deviate. So I'm going to mark this my deviation point. Okay? So if we come back down here, all the way up to there, it's going to be about the same, except right here, notice instead of having that hydrogen, I have two methyls. Okay? So the next step would have been to pull the hydrogen off the nitrogen, right? So if we go back up here, that next step was just a simple proton transfer, right? We got a proton transfer pulled off that second hydrogen. But down here, we don't have a second hydrogen. So this is where it deviates. Instead of pulling off that second hydrogen, our generic base, which could have been the water, could be another amine, is going to pull the beta hydrogen to give us the stabilized enamine. So the last step in a secondary is that we're going to end up with this species. Question about this one? If we did this with an aldehyde, well, let's say we use the cyclic, I'm still going to get the enamine if I did a non-symmetric ketone. I'm going to favor the most stable. Why would this be the most stable? Right? If that's the major, what's the minor? Well, this is the minor. Why is the top one favored? It's the most stable. Why is it the most stable? What's the difference? Both have the nitrogen, both have a double bond. What do you notice about the double bonds? This double bond has how many things attached to it? Well, it's got the nitrogen, but it also has these two carbons, right? How about this one? Just the one carbon and the nitrogen, right? So this one is more substituted, more stable. So the alkene stability is going to favor the internal. There is a way to make the external or the terminal alkene. Book doesn't cover it, and we probably won't see it in this level of chemistry. It has to do with the oxime and a couple of other reagents. But, okay. All right, questions about enamine? Okay. We're going to see enamines again when we get into alpha beta unsaturated reactions. But for now, need to just be able to make an enamine and understand the regioselectivity. The next reaction is a Wolff-Kishner. And the Wolff-Kishner, we're going to actually make a hydrazone. And then we're going to react that hydrazone in potassium hydroxide with heat. And we're going to remove the hydrazone and end up with a ketone. The result is a reduction from a carbonyl to an alkane. So this is an important reaction for that transition, right? We saw a benzylic reduction of carbonyls with Clemmensen reduction, right? When we're dealing with benzylic carbonyls and the reaction with Friedel-Crafts acylation. The nice thing about Wolff-Kishner's reduction is this works with any carbonyl, okay, or any aldehyde or a ketone. Now the mechanism on this one is worth showing in detail if I draw the starting material correctly. So we have our hydrazone. And we're going to put it in a strong base solution. Okay, so the first thing we're going to have is a proton transfer, right? So acid-base reaction. Those electrons are going to go back to the nitrogen. Then we're going to get another proton transfer. This one, we're going to pull, the electrons are going to go down toward the nitrogen, making a double bond to the nitrogen, and then this pi bond is going to pick up a proton. Okay, give me this species. And then we're going to get another proton transfer with the strong base, the potassium hydroxide. In this case, it's not a strong base, it's highly concentrated. So Wolff-Kishner is usually done in a highly concentrated solution. So very low pH. Okay, so that picks that up. Okay, now we have that negative. And the driving force for this last part is the fact that what happens here is that these electrons come around to make a triple bond to that nitrogen. These electrons going right here, the driving force for this is the fact that the byproduct is nitrogen gas. So the entropy here is great. So the entropy is driving this reaction forward to lose nitrogen. And then the last step is a proton transfer. So negative picks up that proton. So I showed a basilic position here, but it will work with other positions. Okay, so give you a little time on the mechanism. So first step, we've made the hydrazone, right? So we get a proton transfer, gives us a negative on the nitrogen. The negative on the nitrogen goes down to make a double bond. And then the pi bond picks up a proton, right? So that gives us this species. Next equivalent base pulls a proton. That gives us a negative charge on the nitrogen. Then the driving force is to create nitrogen gas, right? So it's going to make a triple bond, which makes the nitrogen gas. Electrons go back to the carbon to give us a carbanion. Then that carbanion picks up a proton to give us the final reduction product. And again, this will work with ketones. There is a derivative, there is a alternative synthesis. So you could have one make the hydrazone, two make the do the Wolff-Kishner. You can also put these together in the potassium hydroxide. You'll see that used every once in a while as a reagent mixture, and it's just the hydrazone and step 1 and 2 together. Sometimes it's helpful to do the hydrazone. One of the reasons that chemists will do the hydrazone first is that it turns out hydrazones like to make crystals. So it's a good way to purify your material. So if you do the hydrazone, you purify it, and then you do the Wolff-Kishner. But you can also do the alternative, which is just put the NH2 in there, potassium hydroxide, and heat all together in one pot. Questions about this one? Again, this one, put a star by it because it's synthetically useful. You're going to see this pop up in synthesis. So if we go back and look at these mechanisms, what do we see? Right, so if we see here, we had the base picked up that proton, right? And that base could have been water. And if we wanted to, we could see that that could be reversed. Then if we go up to here where we transferred it off, right? Well, this could have been reversed, right? The water could have attacked that nitrogen. This is reversible, that's reversible, this is reversible, this is reversible, and this is reversible. And what are we losing in this process, right? What have we lost? Well, we've lost, oops, that's not what I want to do. We've lost water, right? Oxygen and hydrogen. So we've lost the oxygen and the hydrogens. So through this process, right, I could hydrolyze this, add water and to these and get them to go back. And that's exactly what happened. So I can hydrolyze these. I can make an imine, go back to the ketone in this case. I could take the enamine and go back to the aldehyde in this case. Same thing with oxine, right? All of these can go backwards to the ketone. Okay, questions about these? So that was nitrogen nucleophiles. So we've looked at oxygen, nitrogen. Let's look at sulfur. We take a dithiol with trace acid. We can end up with a cyclic thioacetal. The thio is the sulfur. So first step, we're going to protonate that. And then our sulfur. Then we're going to get a proton transfer. So we'll pull that proton off. And then we'll get another proton transfer. To the oxygen this time. That gives us a good leaving group. Lone pair comes down, kicks off the oxygen. So we've got loss of the leaving group. Now we got the sulfur. Can attack there, 5-membered ring, kicking the electrons back to the sulfur positive. Then last step, proton transfer to get us to the cycle. Oops. So we end up with the cyclic thioacetal. So similar to what we did with the oxygen. Now the big difference with the sulfur is we have more than one way to hydrolyze it. So we could hydrolyze this back to the ketone H3O plus. But there's also a couple of other reagents, one of them being the mercury chloride. Okay. Mercury reacts with sulfur readily. So sometimes you don't want to just use straight H3O plus, right? Because it may react with something else in the reaction. So if I was doing it with a double bond somewhere in the reaction, that might end up with an alcohol. So the mercury and sulfuric acid, or mercury and TOSH. Right? Can get the same thing, put the sulfur on that and remove it. So this dithiacetal, or the cyclic thiacetal, can behave as a protecting group, right? So we have the cyclic ether, the cyclic acetal can act as a protecting group, and here we can have the thiol. The other reaction with the dithiol is the desulfurization. If I use rainy nickel, which is a preparation of nickel, they bubble hydrogen through it and it gives it, it's very porous. So it's a special way of treating nickel to make a catalyst. What happens here is it reacts with the sulfur, the nitrogen, the nickel reacts with sulfur in a particular way, which reduces the cyclic thioacetal to the alkane. This gives us a way to reduce carbonyls through the cyclic thioketal or thioacetal down to the ketone, right? So we've done, I mean, to the alkane. So we've done a reduction And again, this one is synthetically useful. So put a star by it. So this is comparable to the Wolff-Kishner reaction we just saw. Wolff-Kishner reaction would be good if I had something that had a double bond in it, because hydrogen and Raney nickel is still nickel, and hydrogen and nickel will reduce the double bond. But the desulfurization with the thioacetal would be good if I had something that had a base sensitive reagent in there. We'll see ketones are base sensitive, but we could also have had an acid, or we could have had something that might have substituted with the hydroxide. Okay. So whenever you see multiple ways to do a same synthetic strategy, one of the things you ask yourself is why? And usually it's because there's some reason that one would be favored over the other. And when we get to the synthetic strategies on Thursday, we'll go through more of the examples of why you would pick one of those over the other. Okay. Right. Questions about these? Well, we've done a lot, so let's take a little break. Not a break. Let's change and do try this. Okay. Let's go ahead and take a look. Okay, in this first one, we have a ketone reacting with an amine. What do we need to know about the amine? Is it primary or secondary, right? And what's this one? Secondary amine. Why is that important? Primary amines give us imines, and secondary amines give us enamines. So therefore, the product of this one is going to be an enamine. Okay, and the next one, I didn't explicitly say that there's two equivalents of the methyl thiol there, but the product would be the same, whether I had one equivalent or two. If I had one equivalent, then I'd only get half the product. If I had two equivalents, I would get all of the product. So in this case, I showed the other one cyclic. I showed this one on purpose so that you'd know that you could do the same thing with a non-cyclic. And I'm going to show the hydrogen there so that you won't know we haven't changed that. So I get the thioketal, just not cyclic this time, just the thioketal. Or thioacetal, sorry. Okay, questions about either of these? There are a lot of reactions coming fast. So, okay, let's try two more. Okay. All right, so if we look at this one, right, we're doing the same thing in both cases. So we're taking a aldehyde and reducing that off, and we're taking a ketone and reducing that off. So we're getting rid of the carbonyl. We know there's two good ways to do this with non-benzylic, right? We've got the Wolff-Kishner and we have the thioacetal reduction. If we look at the first one, which of these two would be better? Does it matter about the carbonyl? No, both of these will do the same reaction to a carbonyl. What do you have to look at? You need to look at your other functional group, right? I've got an alkene. Is there any problem with alkenes in mild acid, right, and base? Do we know any reactions where we have, let's say, an organic acid like the TOSH or potassium hydroxide react with an alkene? No, not really. Okay, there's nothing there. We could hydrolyze if we had a lot of water and a strong acid, but not something like the tosylate. How about the thiol and the tosylate? No, no problems. How about the hydrogen on nickel? What will happen to an alkene with hydrogen and a catalyst? It'll reduce down to the alkane, right? So therefore, if I wanted to use these two, and I'll show you what I'm talking about in a second, then what I'd want to use is I want to use the Wolff-Kishners. To get that one. If we look at the second one, we've got the other functional group, right, is going to be this chloride. Is there any problem with having a halide and a mild oops, that's not what I meant to do. An acid? No. How about the sodium hydroxide? What could happen with a secondary bromide and sodium hydroxide? Could I get a substitution reaction? Yes, right? Good nucleophile, good leaving group. I could do an SN2 type reaction. Could I do an elimination? Yes, I could do an elimination. If we look at the other one, is there any problem with the bromide and the sulfur? No, not in general. The bromides and sulfides sometimes react together, but usually as Br2, not as the alkyl bromide. And then HBr, hydrogen and Raney nickel. No, we don't know of any reactions, right? So then, therefore, the second one, what we want to use is the thiol. Right, is the hydrogen and Raney nickel, right? So we use the thiol reduction. So whenever I have more than one way to do something, it's usually not the primary functional group that I'm going to be watching for. It's going to be that secondary functional group. The secondary functional group can direct me whether I'm going to do preference one over the other. There's going to be cases where it could be either, but in this case, they would have given me different products. If I had taken and tried to do the, I'll get my structure right, tried to do this one with the thiol, cyclic thioacetal, followed by hydrogen and Raney nickel. Then I wouldn't have ended up with the target molecule. I would have reduced the double bond as well. If I had done the other one with the bromide, and I had done that one with the hydrazine, followed by the strong base, the Wolff-Kishner reaction, then I would have ended up with these byproducts. Okay, questions about that? All right. I know we covered a lot, but we still have some more to cover today. So we did nitrogen, did sulfur. Now we're going to do carbon nucleophiles. Okay, one of these we've already looked at, which is the Grignard. So remember, the Grignard is going to be the carbon with the mercury. Okay, Grignards always have to react in non-aqueous conditions. That's why I have the 1 and the 2. The first reaction, we get the nucleophilic carbon doing the nucleophilic attack. We got the negative, right? So that's step 1. And then step 2 is the water. We'll get a proton transfer. So Grignards. So we get a secondary, we end up with tertiary alcohol. If we have an aldehyde, we end up with a secondary alcohol. We can also have acetylides. If you remember acetylides, that is the triple bonds. Again, first step, second step. First step is the nucleophilic attack. Second step is the proton transfer. Okay, so carbon negatives will react with the carbonyls. Cyanohydrins are slightly different. If we take hydrogen cyanide, react that with an aldehyde or a ketone, I can end up with a cyanohydrin. Again, this is just a nucleophilic attack. You can make this reaction go faster by adding a little bit of base in solution, such as potassium cyanide. Now, hydrogen cyanide is very dangerous, right? So hydrogen cyanide will combine with hemoglobin, the iron on hemoglobin. What it does is then the cyanide bonds with the iron. Once it's bonded with the iron, it's a non-reversible bond. What happens if you've bonded something that to your iron and your hemoglobin? Yes. You can't get oxygen on it, right? So then therefore you can't get oxygen on it and you suffocate. Now it turns out it's a little bit more violent than that, but that's actually how it kills you. It turns out once it gets into your acid, it makes your stomach eat up and does some other painful things, but it works by actually just suffocating you, the iron. So this is a dangerous one to work with, right? So we usually don't have full bottles of hydrogen cyanide in labs like they had in Jurassic World, Fallen Kingdom. Is that it? My son watches that. They have this huge, huge, huge bottle of hydrogen cyanide that's going to kill. I'm sorry, am I spoiling it for y'all? You wouldn't find that in lab. I mean, that size bottle, I mean, that's just too dangerous. So what you see is that instead of just using hydrogen gas and potassium cyanide, what you'll see them doing is using potassium cyanide and a slight acid solution. So while they'll do this, they'll actually drop in the acid real carefully, seal it all up, right? Add in the acid. When they add in the acid, then the acid and the potassium cyanide makes the hydrogen cyanide. So we make it in situ, right? So you're going to see those reagents. Now, the thing about the hydrogen cyanide is that happens biologically. There are cyanide, not hydrogen cyanide, that'll kill you. But there are molecules that have hydrocyans on them. But it also turns out these can be really useful synthetically two ways. One is reduction. Of the nitrile. So we take the cyanohydrin, we react that with the lithium aluminum hydride, followed by water. Okay, and it has to be lithium aluminum hydride. Sodium borohydride won't react. We'll look at that in the next chapter in detail. But this will make the amine. This is a beta hydroxyamine. Beta hydroxyamines are biologically important compounds. The other thing that you can do with these is hydrolysis. I'm going to need heat, so acid, water, and heat with a cyanohydrin. Now this will hydrolyze the nitrile. So as we'll see in the next chapter, nitriles are part of the carboxylic acid derivatives. They're part of the carboxylic acid derivatives because I can hydrolyze those to get to the carboxylic acid. Now this is an alpha hydroxy acid, right? Carboxylic acid. That didn't look good on cosmetic bottles, right? So therefore, a few years back, they would sell things that had alpha hydroxy acids. Turns out this is an important biological moiety. I'm not sure why they put them in facial products. I scientifically, I didn't look into that. I just noticed they were using them. So, okay, questions about these? All right. So let's step back because I actually missed one. So before we get into the next section, let's step back and look at hydrogen nucleophiles. And this is a little bit of a review. Right, if we take a ketone, we can react that with lithium aluminum hydride, followed by water. That's ugly. Let me give myself some more room. So remember, a lithium aluminum hydride needs to be dry. So therefore we do water in the second step. Sodium borohydride doesn't have the same restrictions, so I can do it in methanol. And I can end up with the alcohol. Okay, so aldehydes will give primary alcohols, ketones will give secondary alcohols. So the aluminum is known as a hydride donor. So the hydrogen attacks the carbonyl carbon. Pi bond is my leaving group. Right, so that's the product of the first. It makes an association with the aluminum. But in the second step, I do a proton transfer. So quick and easy to get the alcohol. So ketones become secondary alcohols, right? Aldehydes become primary alcohols. Questions about these? And these are interchangeable. Lithium aluminum hydride and sodium aluminum hydride are interchangeable for carboxylic acids. I mean, for ketones and aldehydes. For the reduction of this to nitrile up here, I have to use lithium aluminum hydride. I can't use sodium borohydride. Okay, we'll only be able to get started on the next one, but I do think it's worthwhile getting started, which is Wittig's. Wittig reaction, we're going to take a carbonyl and react them with a phosphorus ylide. Unlike the other carbon nucleophile reactions, this one is going to displace both of the, is not going to end up with the alcohol. I'm actually going to end up with a double bond carbon. Now the pH here is the phenyl group. Right, so that pH is the phenyl. So think about that phosphorus has 3 benzene rings around it. So it's got a big bulky side on it. And then these negative positive species like these are known as ylids. So this one is a phosphorus ylide. So if we look at what's happening here, the first reaction we have is that we have the carbon attacking the phosphorus, the carbonyl. But depending on how this is occurring, we can also have, or how stable the illid is. We can also have a concerted reaction at the same time where the pi bond is actually reacting with the phosphorus. And then once we form this complex, then we get another concerted move of our electrons. Phosphorus and oxygen create strong bonds, so that's the driving force here. And so this ends up giving us the oxygen double bonded to the phosphorus, and now a double bond here. This can also be concerted. This can also be stepwise, depending on, again, how stable the negative charge is. If we do it stepwise, the first step is this. Then the second step is the attack of the oxygen on the phosphorus to end up with the same complex. And then the same process here to end up with the products. Now, how do we make the phosphorus? Okay. We react an organo alkyl halide, usually a primary. Secondaries also work, but primaries you'll see quite a bit. We get the phosphorus salt, but then we need to add a strong base, like butyl lithium. The butyl lithium is going to pull off the hydrogen to give us the illid. Then once we have the illid, we can have the illid react and if the illid is not stabilized, we end up with the Z formation, okay, or the Z form, cis Z form. If we look at this illid, right, there's nothing that's stabilizing that charge. But if I look at this illid, right, now I've got that carbonyl there. I can stabilize that negative charge. This one, unstabilized, and most of them are unstabilized, but unstabilized is going to favor the Z form. And that has to do with the fact that they come together and they usually work very concertedly, right? While the stabilized is going to favor the E form. That has to do with the fact that since it's stabilized, it can rotate to give us the more stable product, right? So the Z gives us the most stable transition state. The E is giving us the most stable product, okay? So unstabilized, the transition state drives the products. Stabilized, the stability of the products drives the products.